So with this talk, my goal is to kind of give an overview of some cool things that have been happening recently that I thought were interesting to the game developer audience. I'm going to touch briefly at the beginning of my talk about what deep learning is and why it's so exciting and kind of how I think about the problems that we can attempt to solve using it. And then I'm just going to go into a bunch of examples of cool stuff that I've seen. Some of it's from NVIDIA, some of it's from around the industry and from academic research. So this isn't going to be a super technical talk because we don't really have time. With a title like Deep Learning for Game Developers, I feel like there's like some huge responsibility resting on me to like talk about everything, and it's a big space. So this is going to be a little bit introductory, but hopefully it'll be inspiring and will help you guys think about new ways that you could apply deep learning in the work that you're doing. So I think if you're all here, then you know that deep learning is making a lot of progress in many fields. When I was at Baidu for a couple years, I was focused mostly on speech recognition, and I think natural user interfaces driven by speech and natural language are very exciting applications for deep learning, and we're seeing a lot of progress there. The whole field started out with ImageNet, so sort of image classification. So I wanted to put up this leopard here to kind of remind us of where we began. You know, that was in 2012 when the ImageNet competition really got revolutionized by deep learning. So it's been about 6 years, and we've come a long ways since then. You know, the initial progress in deep learning was we can actually reliably identify objects and images, which is a super hard problem, and you know, many of you may have worked on it at some point or another and discovered how difficult it is. So it was actually quite surprising when we started making such great progress using simple neural nets applied to large data sets. But at the time, you know, deep learning was primarily a sort of a compression-focused task, right? You have an input, which is like a picture, which is, you know, like 1 million dimensions or more than that, and you're going to compress it down to like 1 dimension. Is it a leopard? Yes or no? Since then, over the past 6 years, there's been this explosion of applications, and we see a lot more ways of using deep learning and a lot more different settings, including a lot of generative settings. And I'm going to be talking a lot about those today because I think they're really relevant to game developers. So kind of the next step after image recognition is object detection and localization, and we continue to make progress on that. Human perception is actually a really high bar, and so we're going to keep working on that. But you know, being able to not just identify if an object contains something, but where it is, it's a fundamental problem that has a lot of use. Another thing that there's been a lot of work recently is on generative models for artwork in various ways. This one right here is a picture of the Stanford sculpture garden that's been applied. This has the style of Vincent van Gogh's Starry Night applied to it. So we've basically been able to figure out how to use deep learning to mash styles and images together and generate content. That's pretty exciting. Of course, we had to mention AlphaGo and some of the game AIs that people are developing using deep learning. They've pushed the state of the art forward, and now we have better than human performance on games that we didn't really know we could ever achieve that. And that's thanks to a lot of work at DeepMind and Google that they were able to come up with some really amazing AI for these games. I think it's a natural question to ask, like, how do we apply this kind of technique to video game AI? It's one that I'm really interested in. I do feel like there's a pretty big gap between the state space of Go, which is like a 19 by 19 grid with like black and white dots on it, to a game like StarCraft or something where there's this huge environment and a lot of reasoning ability. So you can't just blindly apply this technology to every problem and expect it to work, but we are making a lot of progress. Okay, so why do we care about deep learning? I mean, it's getting good results, but why is it getting good results? For me, I think there's 3 main points. One is that deep learning is the most scalable machine learning technology that we know of so far. And we can create models that have millions or billions of parameters in them. And a parameter is just a number, like a weight. The goal of making a deep learning model is to search through a big, huge space that describes all the different models with a particular structure that you're trying to use to solve a problem, and find one that works for the thing you're trying to do. And it turns out that being able to create large and complicated models with rich parameter sets actually gives us a lot of power. Now, in the past, people have been afraid about making machine learning models that had so much parameterization because computers like to cheat. You know, when you give the computer a task to solve and you give it the freedom to solve it any way it wants, sometimes what it does is just memorizes things. And of course, that is never good enough for AI, right? Like, it's not good enough to respond correctly to the exact situation you've seen in the past. You need to generalize. And so, in the past, people were afraid of models that had this many parameters because the feeling was they would just overfit, they would memorize, and they wouldn't be able to actually solve real problems. But with deep learning, we've been able to overcome that. Not completely. Overfitting is still a problem. We still run into issues with just memorizing the training set. But there's a lot of techniques and a lot of wisdom that's been developed by the community over the past decade or so that really helps us generalize and solve problems. And having that scale of really rich models with many, many parameters helps us encode really complicated ideas and solve complicated problems. And going along with that, data matters a lot. So deep learning can eat more data. It can productively use more data than other machine learning methods have been able to in the past. I think conversely, there's actually sort of a gap that happens if you have a small problem with not very much data, then deep learning is often not the first thing that you would want to try because deep learning models on small data sets often underperform previous methods. So the advantage of deep learning really comes about when you have big models, big data sets, large compute that you can use to train these models. And then the third thing that I think matters a lot is productivity. So one of the repeated stories about deep learning is that we go into a field where there's been like 100 PhD theses on like very particular aspects of a problem. Say, for example, face recognition. Somebody has figured out how to make the canonical set of face features about, you know, the key points on the face, and, you know, made a taxonomy and, like, you know, sort of an encyclopedic understanding of the problem. And that took a lot of work, and there was some limitations because it was human wisdom encoded in some heuristics that we use to try to solve these problems. And the recurring story is that we go ahead and we replace that with a simple model with a lot of parameters, and we ask the model to learn the representation rather than using human-created features. So in order to do that, we need good productivity because we are, instead of basically, we're providing value by letting the computer learn the right representations, but that means we need to be able to search over them. And so we need efficient software, efficient hardware to do that. And so the deep learning frameworks are really a key part of how we make progress in deep learning. And, you know, if any of you are interested in getting started, there's a lot of resources out there on the web. But learning Python is a good place to start because pretty much all of them are based in Python. My team, we're pretty much a PyTorch team, but lots of other people use TensorFlow and really love it. I think, you know, if you choose one of those two, then good things are going to happen. Okay, so what is a deep neural network? You can think about it as just a way, it's a family of functions that we know how to write down the form of. It's kind of a simple family of functions, and we can use them to approximate other functions. So the building block of any deep neural network is a linear layer that has the parameters in it, has a lot of weights. And basically what we're going to do is we're going to have some set of inputs, and I'll call them X. And then we're going to do a linear combination of those inputs, and I'll call that the linear combination, I'll call the weights W. So that's just a matrix vector multiplication where I'm multiplying X by W. And then that's going to produce some output that then I'm going to pass through a nonlinearity element by element. And we'll call that element Y. And maybe we have a whole bunch of different outputs. And so we can gang them up all together. And the thing that's really cool about this is it's pretty much the simplest kind of nonlinear function that you can think of, because almost all the complexity is in just a big matrix operation, just the big linear projection. And then we follow by these element-wise nonlinearities, and that makes it a nonlinear function. When we stack a bunch of these together, what we're doing is we're composing those functions, and so we're creating a family of really complicated, highly nonlinear functions that then we're going to try to find an example of one of those functions that implements the problem we're trying to solve. Like speech recognition, for example. The input might be a waveform of a person speaking, and the output could be the text of what they said. It's clearly a very nonlinear function, right? So we're going to need the power of this representation, but it's actually kind of surprising because the function that we're choosing here is like basically the simplest possible increment over just a big, huge linear function. So this is one of the strengths of deep learning, is that the functions that we're learning are actually quite simple functions, and it's easy to describe them, and it's easy to compute them. And that's one of the reasons why we can do it efficiently. You know, training a deep learning model can take tens of exaflops worth of computation. And tens of exaflops, I like to equate that to the number of grains of sand on planet Earth. If you go to Wikipedia and look up how many grains of sand are there on the Earth, it'll say there's about 10 exagrains of sand on this planet. So when we're training a neural network, we are doing one multiplier add for every grain of sand on the Earth to come up with the right set of weights that implements this function that we're searching for. And we want this function to have these properties that it generalizes to new inputs that it hasn't seen before, so then we can solve problems like speech recognition. And because it's efficient, because almost all the computation is in these linear layers, and those linear layers are similar to matrix multiplies, we can write efficient kernels for them and make them go really fast on parallel computers like GPUs. And so that's a really important advantage because it allows us to scale. And like I said, deep learning really takes advantage of scale. I've been talking about supervised learning. We use this idea called, or this terminology called supervised learning to describe learning a mapping from X to Y. Say, I was saying for speech recognition, that's like an input waveform to an output transcription. But there's many other kinds of mappings that we could learn. In this picture, I have an example of finding pedestrians. So the input is maybe a window of an image, and the output is, does that window contain a pedestrian, yes or no? So this is just an X to Y mapping. An X is a fragment of a picture, and a Y is, does this contain a pedestrian, yes or no? We call this supervised learning when we have a data set that has a lot of examples of X's and Y's. So a lot of pictures in this case, and a lot of labels about where the people are in the pictures. Then we can think about this as a supervised problem. Supervision refers to a human providing those labels, right? So it's kind of being guided by the ground truth of whatever was put into that data set. And then the goal of training the model is then to search through all the functions that have the form of the neural network that we're looking at to see what's the best one that can learn this mapping, can approximate this mapping well. And it turns out that supervised learning is a really incredible paradigm. You know, you can use it in a lot of different contexts. Image classification is kind of where deep learning started. Speech recognition was also one of the very first applications, and it's one that I've spent a lot of time on. But there's other kinds of mappings that we can learn as well. Speech synthesis is kind of the opposite of speech recognition, right? So given some text, can we produce sound that represents somebody speaking that text? Recommendation systems, so like given the history of a user, the things they clicked on, the things that they looked at, the behaviors that they undertook, maybe playing a video game, can we recommend things that might be interesting to them? That's also a mapping, right? So the X would be their history, their behavior, and maybe also a projected or sort of a projected behavior or a behavior that you'd like to know, like is the user going to be interested in looking at this? You can bunch all those together, that's your input, and then the output is the user interested, yes or no? And you know, all of us interact with these kinds of systems all the time. Like whenever you open a search engine and you type in a query, it's doing a lot of this kind of work, very sophisticated work to learn mappings between your user profile, the things that you wrote down in your query, and all the stuff on the internet to try to find the things that would be most interesting for you. So that's also a mapping problem. And you know, when you use a search engine and you click on a link, then they pay attention to where you go, and they can use that as supervision that then helps them update their mapping. So that's how a lot of these systems work. Natural language understanding, also, you know, if we can create X and Y pairs of text and labels for that text, then we can learn models for that. Or another one for game AI that I think is really important is sort of the game state and the action to a reward mapping. So this is really useful if you're trying to, for example, to implement a policy where you have some sort of agent that's playing a game. You want to be able to predict what's going to happen if the agent makes a particular move. That's also a mapping. So supervised learning, it's all about constructing the space of mappings, figuring out what your data set is, and going ahead and learning a mapping. I think the most surprising thing, and I alluded to this earlier, but the most surprising thing is that we can actually learn mappings that generalize, right? So it's not too hard for a computer just to memorize a table of all of the training examples that you gave it. What's really interesting about deep learning is that it generalizes to things it hasn't seen before. So it's actually learning more than just memorizing the particular inputs that you gave it. It's actually learning how to solve the problem that you care about. Okay. So that's sort of my very high-level overview of how to think about deep learning and what it is, and you know why it's been successful in a lot of different contexts. So now I'm going to start talking about some things that have happened over the past year or so that I found really inspiring and that I thought might be useful to you. And some of you may have seen some of these already before. So the first thing that I wanted to talk about is an instance segmentation project called Mask RCNN. And it comes from Facebook AI researchers led by Kai-Ming He. And the goal of Mask RCNN is to predict basically where objects are in an image. So let's say, for example, you have, here's some example results that came from Mask RCNN. So let's say you have a bunch of people standing in front of a wall and there's a table and a bunch of bottles. The goal of Mask RCNN is going to be to find all those people, draw masks around them so that you have like very tight labels of where each instance of a person is, and then sort of produce the labeled results, describing where all the objects are in the scene. And you can see that the resulting segmentations that it gets are actually quite good. You know, and this particular version has been trained on a certain set of classes, so it knows about whatever classes of objects are in the training set. Remember, it's learning these X to Y mappings. But the resulting segmentations are actually pretty good, and we can do a lot of stuff with those segmentations. For example, in the Mask RCNN paper, one of the things that they do is a pose estimation machine, right? So let's say you had a video and you want to know where the person is and what orientation the person is in, which, you know, for game developers that could be cool because you could make like a controller for a video game that's based on analyzing a video. If you had really good pose estimation that was really solid. So they were able actually to take this instance segmenter and then use it to make a state-of-the-art pose estimator. And there's a ton of other things that you can do with it. One of the things that's really good about Mask RCNN is that it deals well with occluding objects or partially occluding objects, which has often been a challenge for computer vision, right? So like if I took a picture of all of you right now, you know, you're mostly occluding each other. I can see your faces and that's it. So what's the computer supposed to draw? How is it supposed to segment out each individual from the picture of everybody occluding each other like this? That's actually quite a hard problem, and Mask RCNN does better at this than any other approach I've seen before. One of the things that's interesting about Mask RCNN is how it works. So it's actually going to predict several different things. So the X to Y mapping has several different parts. So the input is just the picture, so that's X, but the output Y has three different components. The first is a proposal box So it's predicting where interesting objects are in the scene. That's all that the proposal box is trying to do. Is figure out where is stuff in the scene, can I draw a box around it? And then given a proposal with a box around it, can I classify what's inside that box? Like, does the box mostly contain a person, or does it mostly contain a table, or whatever things we have in our classes? And then once we do that, we also predict a mask for each proposal. So given that box around an object, can I create a binary mask that describes which pixels belong to the dominant object in that box? And so it turns out that by factoring the problem into this way, we're able to train the model a lot more efficiently, and it actually trains much better and gets better results. And so that was the conclusion of MaskRCNN, which just won Best Paper Award at ICCV a few months ago in November. So this is pretty exciting research. Okay, so there was MaskRCNN. I wanted to give you something fun. This is kind of hot off the presses from some of my collaborators at NVIDIA. We decided to take a look at image in-painting, so figure out how we can repair damaged images or remove unwanted objects from images. And there's been a lot of work in image in-painting over the years, but most of them have focused on kind of like square holes, like in the very middle of the object. Can we fill those in? We wanted to be able to handle very irregular kinds of holes. And so we trained a convolutional neural network on a big data set with a lot of GPUs, and the results are actually pretty good. Like this face is pretty damaged, so it's being able to reconstruct all the details of the face. I think it's pretty exciting. Sometimes I just spend a long time looking at these pictures because I think they're so cool. Let me play a video of a simple tool that we made. This is basically just removing stuff. So on the left is an input, and on the right is the output of our neural net. So we're just going to go through and start erasing stuff. In this case, I guess we decided we didn't like the flag and we didn't like the string. We didn't like this rock, so we're going to take away the rock. Interestingly, we left a little chunk of the rock, and so on the right over there, you can see it's kind of not sure what to do over there. We probably need to take more of that rock away. Here's another one. So here's a mountain, and it's a beautiful mountain scene, but I don't like having a road and a bridge in it, so I'm just going to take it out. The next one, we decided to remove a mountain. This is a little bit maybe less kosher. The Sierra Club wouldn't be happy with us for taking away that mountain, but yeah, it just goes away. And then this one, we're going to make this guy look younger by taking away all the character from his face. It does really great until the end when we erase his eyes, and it's a little scary. So I apologize for that. I think this is a limitation of our training set, that we had a lot more women in the training set. So this was trained on a celebrity face data set, and there just happened to be a lot more women being photographed, and so our model likes to draw female eyes. So this is kind of one of the limitations of deep learning, is that your model is only as good as the data that you feed it. But anyway, we're pretty excited about that result, and I feel like if I was making a game and I was working on creating content for a game, having tools like this could be pretty useful. So that's why I wanted to show that one to you. Another one that I think is really cool, also coming from NVIDIA, has to do with ray tracing denoising. So we're pretty excited about ray tracing at NVIDIA, and working really hard. There's some announcements from Microsoft this week about ray tracing in DirectX. And one of the things about ray tracing is that the standard Monte Carlo approaches for sampling the space, you just never have as many samples as you want. You just always want more samples than you have time for. So it's kind of this interesting idea: can I use deep learning to reconstruct the truth given a noisy sample? So can you see in your mind the X and Y pair, the X being the noisy, partially ray traced result, and the Y being the fully ray traced result? this seems like we could train a neural network to do this. And so some people at NVIDIA went ahead and did that. One of the things that they did that I thought was pretty cool was they added recurrence to the model in order to get more temporal stability. So if you're generating a still frame, maybe you don't really care about temporal stability, but if you're generating a video sequence where you're moving through space, you kind of want to be able to use information from prior frames to help you make decisions that are consistent in future frames. And so they added this recurrence to the model, which basically says, I'm going to save the state of the model and I'm going to reuse it. So every frame, I'm not just starting, the input isn't just the noisy frame for my current frame, but it's also a bunch of state that I used when I was reconstructing prior frames, and I'm going to augment my model with that and train the model to use all that together to do this reconstruction. And the results there are pretty good too. I took this picture from one of our blog posts, and you can see on the left, this is the noisy version. So you can see it's like really lacking in samples. There's not nearly enough samples. Which is always the case in real-time ray tracing applications. There's never enough samples. And then on the right is the output after the denoiser, and obviously it looks a lot more complete. But one of the things that's really cool about these sort of deep learning-based reconstruction filters is that they remember a lot of detail from the training set, and so they can actually reconstruct things that if you're just looking at like a signal processing point of view about how much information you have in the samples, you'd have no hope of actually reconstructing it this well. But because the neural network has so many parameters, it can use those parameters to remember salient features about how things look, and then we can use those to reconstruct the result, and we can get results that are quite a bit better than what you could get with standard approaches. Now, of course, there's always a trade-off, right? So the neural network is specialized in some sense. It has a strong prior belief about what things should look like, and it's taking advantage of that prior belief to give these good results. If you were trying to use this for like some sort of forensics thing, like in, I don't know, CSI, a movie or a video game or something, it is going to invent details that match the things it's seen in the past. So there's a lot of bias there. So you have to be careful about that. But for creating video game graphics, you actually want that property. You actually want to reconstruct things that look like the levels that you're trying to play. So I think that's pretty cool. Another related project that I've been pretty excited about has been image quality metrics, so blind image quality metrics to figure out when ray tracing is actually finished. So if you look on the left, there's like a noisy ray traced version of a car, and on the right, it's more of a clear version of that car. It's been converged. If we wanted to estimate how far away we are from convergence, it can actually be somewhat difficult. And so for some professional ray tracing applications where you want like absolute perfection in the quality of your result, it's always this problem of like, well, how long should I let it run? Because it might take 10x longer for one scene than for another. And so if I just do the worst case for every scene, I'll end up spending quite a bit more resources rendering my results. So can we train a neural network where the X is the noisy version of the scene and the Y is sort of an image quality metric that tells us how good is this image? Does it look like it's right? And humans, we know we can sort of do this, right? Like when you look at an unconverged ray tracing image, you can sort of tell this thing isn't quite baked yet. So can we train a model to be able to understand that? It turns out we can. And here's a bunch of pictures of the model estimating different SSIM scores for this scene. So that actually worked pretty well. Okay, I wanted to switch gears a little bit and talk about generative adversarial networks. So far the things that I've been talking about have mostly been this X to Y mapping. We've got an input, we've got an output, we're doing supervised learning. Generative adversarial networks allow us to move a little bit beyond that. It actually allows us to move in the direction of unsupervised learning, where unsupervised learning is the ability to learn things without needing humans to create the labels, which for many applications it's not feasible. So what can we do to solve problems where we actually aren't going to be able to have ground truth for every image or every problem we're trying to solve? And the way that generative adversarial networks operate is that you have two networks. You have one network that we call the generator and one network that we call the discriminator. And the generator network is going to take an input, and it's going to, maybe we should start with the discriminator network. The discriminator network is a neural network that we train to distinguish between true things and fake things. The goal is we want to be able to sort of pair these two networks, the generator and the discriminator, and have them work together to both teach each other how to create better content. So the generator is going to be creating some sort of image. In this case, it's creating this kind of noisy thing in the middle here. It doesn't look anything like a real image. And then we have a library of real images, and we're going to sort of interleave them and feed them to the discriminator and have the x to y mapping on the discriminator be, was this a real image or a fake one? So this one would be, yes, this one is real. This one is, no, it's not real. And then, so as we learn, we are propagating information from the output back through the network. We get to this point, we actually take the gradients here, which are kind of the errors, how has the discriminator figured out that this is a fake image, and we feed that back into the generator network, which then basically lets the generator learn exactly what the discriminator thought was wrong about that image. And so the discriminator then teaches the generator how to make higher quality results. So this is a framework for thinking about applying deep learning that's been really useful in a bunch of different contexts. So let me show you some examples. One of them comes from Berkeley, from Junyan, and it's called Cycle Gann. And what we're trying to do with applying Cycle Gann is we're trying to do image translation without having image pairs. So for example, let's imagine that I have a picture of mountains in the summer, and I want to translate that to pictures of the mountains in winter. Now, I may not actually have paired images from the exact same viewpoint for every single mountain that I'm trying to learn, right? I have maybe a lot of pictures in the summer and a lot of pictures in the winter, but there's no correspondence. There's no direct X to Y mapping. But what we can do is we can make a generator that can take an image from summertime to wintertime, for example. And then we have another generator that goes the other way, that goes from winter back to summer. And so with Cycle Gann, the idea is that if we take it through a full cycle, so we go from summer to winter and then back to summer, that the difference between our original summer image and our fake summer image that's been through winter should be small, because we've gone in a cycle. And similarly for the other one, from generating, let's say we started in the winter, we go to the summer, and then we go back to the winter, the difference between our two winterized images should be small. So what this allows us to do is formulate image translation problems without ever actually having pairs of images. And then so you can do things that are pretty cool, like turn zebras into horses and turn horses into zebras. Or go back and forth between summer and winter, or go back and forth between a picture of the real world and a Monet photograph. We don't have paired, we can create a lot of images, and for all of them, except for a vanishingly small percentage, there's no corresponding Monet drawing of that scene. But we have enough Monet images that we have some body. We can use this Cycle Gann idea to actually construct these correspondences, and then we can translate. If I was, for example, a game developer, I would really want to think about using image translation to make content better, because I think it could make translating content, say from one level to another, much easier if I was able to train some models to help me do that. So I think it's a pretty cool idea. Another one that got a lot of attention last year was called Progressive Gann, and this was also from NVIDIA. And the goal here was to create fake images that are generated completely by random numbers that look like real images. And GANs in the past, when we've asked them to create images from ground zero, have sometimes had a problem. Well, they've always had this problem that their resolution is just not very good. And so the idea with progressive Gann was, well, let's make it easier for the neural network by starting with a really small and simple problem. So let's imagine that we're only going to make an image that's 4 pixels by 4 pixels big. Right? And all we have to do is make a generator that can take random numbers and generate a 4x4 picture that looks like this. And then we have real 4x4 pictures that have been downsampled a whole bunch, and then we feed them to the discriminator and then train that for a while until it gets pretty good at making 4x4 pictures of faces. Well, then we'll add one more layer in that upsamples it to 8x8, and we'll refine it. And progressively, we'll continue adding layers to this problem until we get up to 1024 by 1024. And then you get the results that we see here, which I think are actually quite compelling. When I look at these pictures, it's very hard for me on many of them to realize that these were generated by random numbers and a neural network. These are not actual real celebrities. So imagine what kinds of content you could create for your games if you wanted to. If you can figure out like a corpus of images and you can put together tens of thousands of images of something, you can train a model to create more instances of that thing. It seems like a really interesting idea. Another project that I'm pretty excited about that actually took place in my lab is rendering photorealistic images from semantic labels using GANs. And this work just got accepted at CVPR, so it'll be presented in July at the CVPR Computer Vision Conference. This project tries to make high-resolution photorealistic scenes given only semantic labels. So what does a semantic label look like? So here's an image from the Cityscapes data set. So there's a bunch of cars. You can see the cars are blue. The road is kind of this dark pink or purple color, and the sidewalk is a bright pink. And there's some street signs and some trees and buildings and sky. And so here's the result of our neural network. And there's a bunch of things that I think are really remarkable about this. We haven't told it, for example, how to draw a curb. If we go back here, there's no details there about where the geometry of the curb is. We're just giving it a very coarse indication that, oh, there's a sidewalk, and next to the sidewalk there's a road. And then the model figures out, oh, whenever that happens, I need to draw a curb. It goes ahead and does that. It figures out that whenever there's a street sign, so you look at all those yellow things, those are all street signs, but they have different shapes, right? Like the upside down triangle, that represents a yield sign. Whereas like the X, I think that's like a railroad crossing sign or something. So at least for the upside down triangles, our model kind of draws a yield sign in there because it's recognized that anytime you see a sign and it's upside down triangle, it needs to be painted like that. So it's learning a lot of detail just from these pairs of images that we're giving it. Here's another example of another road scene and the results from our network. One of the things that I think is really cool about this is that we can actually control the result, so we can control the rendering. So this road, this cobblestone texture, we actually forced that by clustering our data set. So we went through the data set and we clustered all the different roads, and then we took some of those clusters and forced them into the middle of this neural network when it was doing the generator for the generator part of this Gann, and we actually can make it look like cobblestone. So what that allows us to do is, this is a step towards a rendering engine, a graphics engine that is based on a neural net to do the rendering, right? So imagine you had a video game engine who is drawing pictures like this, keeping track of objects in 3D space, but at sort of very high levels of granularity, like where's the cars, where's the road, where's the sky? And then you train a model to actually do the rendering, then now we've made the task of generating graphics a data task rather than a traditional rendering task. We can actually just sample a lot of examples and go ahead and train them, and then we should be able to recreate environments in different places without having to change the graphics engine at all. Just drop in a different model that was trained on a different place. So let's say, for example, I wanted to make a level of a game that was like inside the Moscone Center, I could wander around, take videos of stuff in here, segment them automatically using mask-RCNN or something like that, and then use those segmented images to train one of these models. Now I have a way of generating any sort of scene that I want inside the Moscone Center. I can move the people around or the cars or whatever. And then imagine that I wanted to go do that in a different conference center. I just take a video in there and then train another model on that. That's the kind of thing we'd like to move towards, and I'm pretty excited about that. We're not there yet. There's still, obviously these graphics are like convincing for a few seconds, but there's something like a little bit wrong about them still. So we still got more work to do. Although I think it would be fun to play a game that looked like this. It might have an interesting style. Okay, I don't want to run out of time here, so I'm going to talk a little bit about some other kinds of problems. So there's a really interesting paper that came out last year about unsupervised learning for text problems. And it was about learning, the title was Learning How to Generate Reviews and Discovering Sentiment. It was written by Alec Radford at OpenAI. And what they did was they trained a model to reproduce a text data set like 40 gigabytes of Amazon reviews, for example. And the model's goal is just to reproduce that character by character. So it doesn't know anything about the high-level content of the reviews other than it's been given 40 gigabytes and it's been asked to predict what the next character is given the past characters in that review. Well, it turns out that in order to do a good job of predicting what the next character is, the model needs to learn how to predict what the next word is. And in order to predict what the next word is, the model needs to predict other things about what the person is saying. And so it needs to actually understand a little bit about the context of what's actually being said in the model. And so then what you can do with that is take that model, it can consume some text and process it, and as it does it, it builds up its internal state that represents what it's seen in the past. You can then take that output as the output of the model and give it to another model that has been trained with just a little bit of data to solve a particular task like sentiment analysis. So let's say, for example, I want to figure out, like, is this text expressing a positive sentiment or a negative sentiment? It turns out that with very little labels, like only a few hundred labels of this text is a positive sentiment text, this is a negative sentiment text, we can transfer the representation that we learned from our unsupervised character prediction model to the sentiment analysis task. And that's actually what is being shown in these graphs. So in this graph, what it's showing is that for negative text, the output of the model is sort of in this negative range, and for positive text, the output of the model is sort of in this positive range. So we could draw a line somewhere and say, as long as the output of the model is above or below the line, then we're going to say it's a negative or positive example. And that's how these things sort of work. And so surprisingly, it turns out that this works pretty well. In fact, we're busy applying this sentiment analysis to various problems at NVIDIA because it turns out that the results that we get from this sentiment analysis are actually better than some other commercial tools that we've used in the past. So for example, on here, I took some tweets that represented things about gaming and ran them through our model and compared them with this other commercial tool. I only put some tweets up here that our model correctly identified as positive or negative and the other commercial tool failed on. And I think one of the reasons that these other tools often fail is because they don't understand the context as deeply as this model does. So like this one saying E3 is so dope, new Assassin's Creed looks lit, and PUBG also looks insane for console. Well, like insane, that's not a good word. Like most of the time, insane is correlated with bad sentiment. Or dope, like also like most of the time, it's not such a great thing. Lit. This is a thing that might not have even been in the training set for this other model, right? Because if it's based on words and just sort of tables of probabilities, there's a lot of things that just might not be there. But our model figured out this is actually a good thing. Here's another one I think the competing model said it was bad because it had RIP in it, and like RIP is associated with some really bad things. But yeah, so our model is able to generalize and solve the sentiment problem better than a lot of commercial tools out there, and it was actually very simple to construct. We just needed a bunch of GPUs and a big data set to train a big model on. This is kind of showing our error rates as we make the model bigger. So if we had a small neural network that only had 256 neurons in it, then our error rate was almost 50%. This is the quiz part. 50% on a binary sentiment task, what does that mean? It means failure. It means complete and utter failure, because you can flip a coin and you'll get 50%. So then as we make the model bigger, then we see it gets dramatically better. And so that's been really interesting for us, that these kinds of models, they just need a lot of parameters to understand what's going on. Okay, and then the last example that I wanted to show before we take a few questions is text-to-speech. So last year, Google and DeepMind came out with this WaveNet way of having a neural network generate speech samples directly. So the input is going to be linguistic features that are derived from text that you want a computer to be able to say, and then the output is going to be the actual samples of the waveform. And so here's some examples. You may have heard these already. In fact, the WaveNet is now deployed in Google Assistant. So Google Assistant, if you use that, then you've heard this neural network in action. Let's see if we can make it sound.
Fidelity.
That was
Single WaveNet can capture the characteristics of many different speakers with equal fidelity.
Okay, so that was a non-WaveNet version, and you could feel there's a little, there's transitions that weren't quite right. It sort of felt pieced together. The WaveNet is actually going to synthesize it completely, and it sounds a lot more natural because of that. Let's see.
A single WaveNet can capture the characteristics of many different speakers with equal fidelity. Now, it's fast.
Okay, so why did they say now it's fast? Well, it turns out that the original WaveNet paper that was published last year was very difficult to deploy. It is so computationally intensive to predict each sample. And remember, for speech, that needs to be done like 16 or 24 or 48,000 times per second, right? You need to make a new sample a lot. It was just way too expensive to do that, and it was very sequential because the original WaveNet was autoregressive, so every sample depended on all the prior samples that it had predicted. So this new WaveNet, it's a parallel WaveNet, so it's 3 orders of magnitude faster to do inference on, and it sounds just as good, so they went ahead and deployed it. So that's pretty exciting, and if I was a game developer, I think having better TTS could make games a lot more fun to play, and there's been a lot of advances there. And one of the things that's great about TTS as well is that it doesn't actually require that much data, because if your goal is to produce the result sample by sample, even a second of audio has 16,000 samples in it. That's already a lot, right? So if you have on the order of 20 hours of a person speaking, which isn't that expensive to get, you can train a custom TTS model for that voice, and it can sound pretty good. So I feel like there's a lot of excitement about TTS, so I wanted to highlight that.
A single WaveNet can capture the characteristics of many different speakers with many different fidelity.
Too many computers. Okay, so that's the end of my talk. I guess what I was hoping to get across to you today is deep learning can be used in a lot of different contexts. There's lots of cool ideas. I just took kind of randomly some of my favorites from this year and wanted to show them to you and hopefully inspire some of you to start applying deep learning to the process of creating or managing or constructing the games that you work with. And I find all the work you do really inspiring. I love games, so it's fun for me to come here and talk to you guys about that, and I hope deep learning can make a difference in your work. So thanks.